For our final application, what we're going to do is look at what's called the binomial formula. So this can actually provide us a really nice formula that allows us to quickly expand powers of binomials, so of things that have two terms. And so if we look at this question here, the first couple are hopefully a little bit easy for us. We have x plus y to the 0. Anything to the 0 is just basically going to be 1. So that one's easy enough. X plus y to the power of 1. Well, anything to the power of 1 is just itself. X plus y squared. And so if we do this one, hopefully you know this, or at least it's familiar to you. X squared plus 2xy plus y squared. And so I'm just going to call attention to basically the coefficients of everything here. What we've got is 1. For x plus y, we could write that as 1x plus 1y. And then x plus y squared, we could put some 1s there. And then maybe write the 2 in pink as well. And then a 1 there. If you're seeing those numbers, hopefully that pattern does jump out a little bit at you. And so what I'll do is work out the other 2 at the side over here. And so if we do x plus y cubed. Now, what I'm going to do with this x plus y cubed is we'll write it as x plus y times x plus y squared. And we already know the x plus y squared is x squared plus 2xy plus y squared. And then to expand that, what we'll do is distribute the square term, the x squared plus 2xy plus y squared, across the x and the y. And I'm going to write it in a particular way, but what we'll get is x cubed. So x times x squared plus x times 2xy plus x times y squared. And then what I'm going to do is do the y across all the terms. So the first one will be x squared y and 2xy squared. And the y squared times y will be y cubed. And so the way that I've written it, just because of the way the x's and y's have their pattern here, is that you can see that the columns are actually like terms. So I get to just add everything together. So I get x cubed plus 3x squared y plus 3x y squared plus y cubed. And so I'm going to write that over on the left here. But again, hopefully you're seeing those numbers. Right, I've got a 1, 3, 3, 1 for my coefficients. Should jump out at you. X cubed plus 3x squared y plus 3xy squared plus y cubed. And if you're looking at where that 1, 3, 3, 1 comes from, basically, yeah, if we look at every single term, like for example, this 3 here is coming from the y times the x squared term plus the x times the 2xy squared, the 2xy term. So what we're getting is the x plus the 1 here plus the 2 there are adding up to the 3. So this 1 here plus 2 there are giving us that 3. And then the next one, this 2 plus this 1 are giving us this 3 here as well as we make our way over. We're going to see the exact same thing with x plus y to the 4. So this is x plus y times x plus y cubed, which we already know. So x plus y, and then I've got my x cubed plus 3x squared y, 3xy squared plus y cubed. And so if we work this out, same deal, I'm going to push the x through the whole thing to get x4, 3x cubed y, 3x squared y squared plus xy cubed. And I'm just going to move that over a little bit because I do need another term in there. And now if I push the y through, I'll get yx cubed plus 3x squared y squared. And the 3xy squared times y. And then finally, the y and the y cubed will give us y4. And so again, when we add those up, it ends up just being essentially that every term is taking from sort of the two terms above it. So we get x4 plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y4. Again, those coefficients, if you're not paying attention, what we've got is actually Pascal's triangle here. So we've got x4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y4. And so that pattern is actually going to hold through consistently. And so what it gives us is what's called the binomial formula. And so I've written out the binomial formula here with a and b instead of x, y, but hopefully you can still kind of see the pattern. And so in general, for example, if we have any expansion, so let's say like, for example, the power of 4. So that power of 4 is going to be the highest power that we start at with the x or the a. And then what you'll see is as you make your way across, the powers of the a's drop by 1 every single time. And so you have n minus 1, n minus 2, etc. Oh, sorry, underlined the wrong one there. And then alternatively, the powers of the y start at 0 and then make their way up to 1. Oh, I did actually both of them backwards there. 1, we'd have 2 for b squared, y cubed, the next one will be b cubed, and then all the way up to basically our n value, whatever that is. And then these coefficients here, they are your choose formulas, which I've also been calling kind of at the same time the binomial formula. And this is why, because this is where these numbers are coming from. So yeah, they're just the things that are in Pascal's triangle. So those are the exact same numbers. And so they all kind of coincide, which is great. And again, just watching the pattern as you make your way left to right, it starts at 0, 1, 2, 3, all the way up to n. And so that's the pattern to watch out for when we plug things in. The powers along the bottom of the binomial formula start at 0 and go up to n. The powers of your first term start at n and go down to 0. The powers of your second term start at 0 and go up to n. And so what I've added is a second version of the exact same formula. So this is just in something that's called summation notation. There's sort of a general form for all of the terms as we make our way across. All of these terms have a very precise pattern to them in that numbers go up by a certain amount or numbers go down by a certain amount as we make our way left to right. And so this is going to describe that general pattern as we go from a 0 term to an n term. So if you haven't seen that before, I'm going to try to familiarize you to it a little bit. You can mostly avoid it, but there will be some questions where using this summation formula will save you a lot of time and energy. Okay, so we're going to start with maybe a slightly easier, a longer one, but a slightly easier one of this x plus 3 to the 5, and then using this expansion formula. So I'll use both versions of the formula to hopefully try to get you a little bit familiar with how to use the summation. So if we want to use this formula, what I'm going to do is identify my a, b, and my n. So here I will have a is x, b is 3, and n is 5. And so if I were to plug those things in and write out the formula, so what I would do is start with my n is 5 and then 0, and my a is x, and then to the 5. And then, yeah, so just make my way across term by term. So this is the first term with the 0 in it. And then my next term is that one with the 1 on the bottom. So it'll be 5, 1. The power of x goes down 1. And the power of my b, which in this case is 3, is going to go up 1. And then 5, 2. Power of x goes down 1. Power of b goes up 1. And then I basically just keep going until I get n choose n, until the top and the bottom number are the same. So 5, 3, x goes up 1, 3 goes, sorry, nope, I'm doing that backwards. X goes down 1, 3 goes up 1. 5, 4, x goes down 1, 3 goes up 1, and then finally 5, 5, x goes down 1. So I can just not write it. If you'll notice in that last term, I didn't even write an a there. And b goes up 1. So that's expanded. So the next part is going to be to simplify. So generally what simplify is going to mean is no brackets. That includes that binomial bracket. So I need to evaluate all of these things. So 5 to the 0 is going to be 1 x5. And then 5 to the 1 is going to be 5 x4 times 3. 5, 2 is 10. So I'll get 10x cubed times 9. 5, 3 is also 10, so 10x squared. And then 2 to the 3 is 27. 5, 4 is 5. And then I'll get x times 3 to the 4 is 81. And 5, 5 is 1. And 3 to the 5 is 243. And so I'm just going to clean this up by tidying up those numbers. So I have x to the 5 plus 15x4 plus 90x cubed plus 270x squared. 5 times 81 should be 405x, and then plus 243. And so if you've done it right, you should notice that pattern with the x's of the powers. So we can see the powers are 5, 4, 3, 2, 1, 0. Definitely check for that. So what I'm going to do now is also solve it using the summation notation. Should hopefully get the same thing. I just want you to get a little bit more familiar with it. So what we would have here, we have the same n, the same a and the same b. So I'm going to plug those in. So I'd have the sum of k equals 0 to n equals 5. And 5, choose k, a to the 5 minus k, and b to the k. So what's going to happen here is k is going to take on different values every single time. So what we're going to have here is this is our general term. And we're going to plug in k equals 0. So that's that first value, which we get from the base. And that tells you where to start. So I'm going to actually move that. Yeah, so we'll plug in k equals 0, and then k equals 1, 2, 3, 4, and then 5. And then we know to stop at 5 because that's the number along the top. So you're just counting 0, 1, 2, 3, 4, 5. And so we're going to plug those numbers into that general term. And that's why there's a k in there, because it tells you where to plug these things in. And so if I do these expansions, I'll get the first one, k equals 0 will be 5, 0. So my a to the 5 minus 0. Actually, I'm just going to go through and change the a and the b into my x and my 3 at this point. So that'll be x and the 3. So again, that's those same substitutions. X, a is x, b is 3, n is 5. So instead of a there, I'm going to use that x again. And then that'll be 3 to the 0, right? So that's the k equals 1 term. And so just to tell you where I got that, this is k equals, sorry, not k equals 1, k equals 0. And then basically what we do with all these things is then add them all together. That's why it's called summation. So it's used for like a series of things being added together, specifically when there's a pattern. And so I'm going to plug all these things in. My next one will be k equals 1, k equals 2, k equals 3, k equals 4, all the way up to when I'm told to stop, k equals 5. And so the next one's going to be, let's say 5, 1, x to the 5 minus 1, 3 to the 1. We put a plus between them all. 5, 2, x to the 5 minus 2, 3 to the 2. 5, 3, x to the 5 minus 3, 3 to the 3. 5, 4, x to the 5 minus 4, 3 to the 4. And 5, 5, x to the 5 minus 5, 3 to the 5. And hopefully you can see that this is exactly the same line as we have up here. It's just kind of telling you to do the same thing in a slightly different way. All right, so just for a slightly harder one, now what we're going to do is expand and simplify 2x cubed minus 5 to the power of 3. So you could just totally use like your expansions and multiply this out, but this formula is going to be a lot faster for us. And so what I'm going to do is, just start with, I'm going to do the summation notation. So this is going to be sum k equals 0 to n choose k, a to the n minus k, b to the k. And what I'm going to do is sub in my a, n, and k. So this is n. And 2x cubed is going to be a. And then the minus 5 is going to be b. So we need it to be minus because this formula is written for an a plus b. So that's going to tell me where everything goes. So I'm going to have sum k equals 0 up to 3. 3 choose k. And then 2x cubed to the n minus k. N to the 3 minus k. And then minus 5 to the k. And so same as before, what I'm going to do is just plug in 0, 1, 2, 3, add them together. So I'm going to write that out. K equals 1, k equals 2. No, that starts at 0. It starts at 0. Then k equals 2. And then k equals 3. So we just plug them in exactly where those k's are. So x is going to stay in there. X is going to be like stay as a variable. So I'm going to have 3, 0. 2x cubed to the 3 minus 5 to the 0 plus 3, 1. 2x cubed. And now I'm going to have 3 minus 1, which is 2 minus 5 to the 1. 3, 2. 2x cubed to the 1, right? So that power goes down by 1. The other power goes up by 1. And then I'll have 3, 3. The 2x cubed power goes down by 1 to 0. And the minus 5 power goes up by 1 to 3. And then the simplify tells me to evaluate all of this and get rid of all those brackets. So I'm going to have 1 times 2x. So I have to do that 2x cubed. So that's going to be 2 cubed is 8. And then x cubed cubed, remember by power rules, we multiply those powers to get 8x 9. And then negative 5 just vanishes because it's the power of 0. And then plus 3 choose 1 is 3. So 2 squared is 4. And then x cubed squared is x to the 6. And then times minus 5. 3 choose 2 is 3. And then I'm going to have 2x cubed to the 1. And then minus 5 squared is 25. The negatives will cancel. And then 3 choose 3 is 1. 2x cubed is 1. And negative 3 to the 5 is negative 125. And now I'm just going to tidy those numbers up. I will get 8x 9. 12 times negative 5 is minus 60. X to the 6. 3 times 2 times 25, so that's 3 times 50 is 150. X cubed, and then negative 125. And so, so that should be it. That's my answer. Again, notice that the pattern of the powers here are completely linear. We've got the powers of x dropping by 3 every single time, 9, 6, 3, 0. if we had a y in there, so if I snuck, let's say, a y right here, maybe even like a y squared to make it more interesting, I could sneak that in all of these answers. It's not really going to do too much to the structure of this. What I'll end up getting here is a y squared. When I do the y squared squared, I get y to the 4. Y squared cubed is going to be 2 times 3 is 6. And what you would see with this pattern is while the x's drop by the same number each time, the y's should go up by the same number each time. So y to the 4, y to the 6. Right, so they go up by 2 each time. All right, so one last type of question, and this one's a little bit harder, but it's all kind of the same idea. We're going to find the x to the 12 term in 3x cubed minus 4 to the 6. I just changed my mind. I'm going to actually make it 3x cubed minus 4 to the 10. So the reason is I don't want you to be tempted to actually find this giant, it's actually going to be an 11-term polynomial. So there's going to be a faster way. And so the fastest way is going to be to use the general term. And that is actually just the thing in the summations. So we're going to use the general term to find which one has x to the 12 in it. And so each term basically is going to look like that formula there for the general term. So that n choose k, a to the n minus k, b to the k. And then if I'm following the pattern in there, I know my n is 10. I don't know k yet. A is going to be 3x cubed. And then I know my n is 10, so I still don't know k. And then b is going to be this minus 4 to the k. And so what we're going to be looking for here is essentially solves for k. And if you look at what's going on with these numbers, this 10 choose k is just a number. Negative 4 to the k is a number. This is the only thing that has x's in it. So what we're going to do is just clean that chunk up to find the k that we need to get that power of 12. So if I just take that part there, so if I expand that 10 to the k, what I get is 3 to the 10 minus k, which is just a number. And then x to the 3 times 10 minus k, if I follow my power rules and I apply that to the x term. And so what we want is equals something times x to the 12, right? We don't know the coefficient. That's actually kind of the whole point of this. And so to make that work, basically we need 3 times 10 minus k to be equal to 12. And we should be able to solve that. That means that 10 minus k is 4. And so that means that k is going to be 6. So we know that k is 6. So now what we're going to do is actually just plug that into the general term. And that'll give us our coefficient. So now that x to the 12 term, if I chose the wrong k, I won't get x to the 12. So I'm going to get 10 choose 6 times 3x cubed to the 10 minus 6 times negative 4 to the 6. And these numbers are going to blow up. So 10 choose 6 is 210. And I'll get 3x cubed to the 4. And 4 to the 6 is 4096. And the negative is going to vanish with the even power. I'll just clean this up a little further. 210 times 4096 is 860,000. 160. 3 to the 4 is 81. And then that 3 to x cubed to the 4 will be 3 times 4, 12. That is the power that we wanted, which is good. And I'm going to multiply those coefficients. We're going to get this massive number, 69672, 960 x to the 12. So that is the x to the 12 term. So yeah, so the whole goal is basically find that coefficient, and there it is. You definitely could have done this by actually finding the whole expansion for that 3x cubed minus 4 to the 10. But you would have gotten like 11 terms that all have big, ugly numbers like that, and you probably would have gotten pretty bored of it fairly quickly. So this is just a bit of a shortcut for that. That should just about wrap everything up.